Hello, my name is Antonis Papayanu, and I'm a postdoc researcher at the Institute of Computer Science of Forth. This video is a brief overview of our proposed solution to the DEBS 2022 Grand Challenge. This is a joint work with the master student Stefanos Kalogerakis and Professor Kostas Magoutis. We are Group 14. Let's start with an overview of the data analysis pipeline and the software stack used. Our proposed architecture relies on three major components: a data ingestion and reporting process, a data processing task that runs on top of the Apache Flink stream processing engine, and we also use the Apache Kafka to persist the incoming data and the analysis results. Kafka also allows to decouple the ingestion phase and simplifies the integration of the platform used for the challenge. Now, let's see how data flow from the challenge source through our analysis platform. First, our ingestion process fetches data from the challenge platform using the gRPC protocol and stores them in a Kafka topic. The analytics task that subscribes to that topic ingests data and performs the analysis, and it finally publishes the results back to Kafka. Finally, the reporting process sends data back to the challenge platform. We have put a lot of thought in designing a rate control mechanism in the ingestion service. So here we have a typical trade-off between latency and throughput, and we have tuned the rate control mechanism to achieve a balance between these two performance metrics. Now, let's move to the analytics job. The analysis is performed on top of the Apache Flink stream processing platform. The interface between Kafka and Flink is based on the Flink-supported Kafka source and sink operators. And it's time to focus on the application structure of the Flink job. Here we show the operator's pipeline of the Flink application. To start, we have the Kafka source operator that ingests data from the Kafka topic. And then we have the unpack operator, which unpacks and emits to its output the symbol events included within the batches. The operator also injects metadata that are used by its downstream operators. These metadata include the last timestamp of each unpacked batch and the flag that indicates the last event per symbol within the batch. The operator also injects metadata regarding the symbols that are marked for lookup and the number of all the lookup symbols in the batch. Now, the output of this operator is partitioned on the symbol ID. The unpack operator follows a window operator that calculates the last price of a symbol within a 5-minute time window. So the challenge here is how to handle late and out of order events. Typically, events that arrive late after the window has closed will be dropped, and so they will be ignored by subsequent EMA calculations. Flink, the Flink built-in window operator supports allowed lateness, which prolongs the time that a window can handle late events. However, the question still holds. How much time do we have to set lateness duration? And what if we have events arriving later than the prolonged window duration? This does not guarantee that we won't drop events. One way is to live with it, but we decided to build an application that reports correct results. And so we choose to build our own custom window operator. We do guarantee that there won't be dropped events. Our custom window maintains minimal state for its 5 minutes time windows. That is the last price of a symbol along with its timestamp. We also keep track of the processed batches, whether or not there are unprocessed symbol events in the batch. Now, having our custom window operator, we have to implement the logic to specify in which 5-minute time bucket belongs its incoming event. To do this, we use a simple formula that uses the timestamp of each incoming event to derive the start time of the corresponding time bucket. So the major challenge of our custom window is to decide when it is safe to close a window and emit the last price of a symbol within a 5-minute time bucket. This means that we have to identify that we have processed all events up to a timestamp, and so there won't be any out of order late events that will arrive after the window closes. To do this, we keep track of all the processed events for each batch. Now, keep in mind that there is a separate window instance per symbol, and for each incoming event for that symbol that the operator processes, we check if we can safely close a 5-minute time bucket. So let's see how these checks work through an example. So for each symbol, a window instance maintains the status of its 5 minute time bucket. It also holds metadata regarding the progress of event processing per batch. Using the injected metadata from the previous operators, we can specify which time buckets are affected by the batches. This is by using the last timestamp of the batch. For example, here we see that the last timestamp in the batch 5 is 12:23. So we know that batch 5 can affect up to this specific time bucket. Now, metadata also used to mark the last event for a specific symbol in a batch. This allows the custom window operator instance for that symbol to identify that it has processed all events in the symbol in the batch. As events can arrive out of order, the window marks the completed batches with no specific order. The important property here is that when the operator marks a continuous range of batches as completely processed, it can safely close the affected buckets, time buckets, up to that bucket. So in this example, we can emit the results for the time bucket 12:15 to 12:20, as all subsequent batches does not affect this bucket. The custom window operator emits the last price of the symbol for the 5-minute time bucket. So based on this, the following operator can calculate the EMAs for the symbol as requested by the challenge. And having the EMA, we can report the query 1 results. The input stream of the Q1 reporter is partitioned on the batch ID. So the reporter gathers all the results for all lookup symbols in the batch and publishes the results in Kafka. The output of EMA calculator is also used to discover crossover events. This stream is partitioned on symbol ID and consumed by the crossover calculator operator. This operator discovers crossover events as defined by the challenge, and it also maintains a list of the last 3 crossover events for the symbol. Finally, the query2 reporter, similar to the query1 reporter, gathers query2 results for all lookup symbols, and it finally writes the results to Kafka. And finally, our reporting process subscribes to the query 1 and query 2 result topics and reports back to the challenge platform. And here we show the code organization in the repo. Our repository also includes an automation script that can be used in order to install the necessary software components, to build the application from source code, and finally run the analytics pipeline. The processing application can be configured using the following configuration settings. With I and J options, we can specify the parameters of EMA calculation formula, and with the Q, we can define the queries that we are interested in. So we achieve good reconfigurability, which is required by the challenge, but we also support scalability and operation reliability. Finally, we would like to thank the DEBS 2022 Grand Challenge team for proposing this very interesting and exciting challenge, and also for supporting us through our implementation and evaluation effort. For more information or for any question, please do not hesitate to contact us. So thank you.